Our next session is session 120, Prompting Progress, Integrating LLMs into Statistical Research. Our first speaker will be Dr. Lucy D'Agostino-McGowan. Lucy, if you're here, you want to share your screen and get going?
I do. My video is disabled, but I
Okay, no
can,
worries.
yeah, I put a note in the chat, so hopefully the moderator, oh, they're not gonna let me share either. So, okay,
Um,
let me see.
Let me promote Daphne as well. There you are.
It says, oh, okay, now it's gonna, let's see, replace current share. Yes, now it's letting me, perfect. I don't know, and my video, okay, so looks like we're good. All right, excellent. Thank you, Sarah, for the introduction. So today I'm gonna be talking about, very briefly, I think these are 10 minutes, right? All right, yeah, about exploring the potential of large language models in generating saturated DAGs for causal inference, and I'll define some of those pieces here in just a second. If you are interested, you can find these slides on my website at lucymcgowan.com/talk. Okay, so one of the main pieces in this talk title is the jargony term DAG, and so I thought I would just define it in case folks are not clear. So a DAG is a directed acyclic graph. This is often a way that we like to kind of explain causal relationships pictorially. So typically you have nodes, which are like these circles here. These usually represent like variables or features. And then you have edges, which are arrows between the nodes. And essentially like drawing an arrow between two nodes indicates that we think that the data generating mechanism is such that the node on the left causes the one on the right. So basically, it's just a way to describe the assumed data generation process, which is really helpful in causal inference because when we are trying to answer causal questions, we have to have this correct in order to, like, all of our assumptions are sort of predicated on us understanding the data generation process accurately. And so DAGs are a nice way to basically be able to communicate across different disciplines. So as a statistician, we could write out our assumptions mathematically, and you can kind of back into what the assumptions are based on what things you adjust for in a causal analysis. But I find, especially for collaborating across different disciplines, these visuals make it really helpful to be able to sort of make sure we're all on the same page. And so ultimately it influences the causal effect estimation choices. So how we estimate those causal effects is often driven by the DAGs themselves, or these assumed pieces. So what happens now when I am working with a collaborator on answering some kind of causal question with observational data? A lot of times it's something like this, where this is me up here and this is my collaborator. And I'll say, draw the data generation process, and they'll be like, what? And so we're sort of starting with a blank piece of paper, and sometimes that's kind of hard. And so then I will say something like, okay, I'll start, and I'll say, we're assuming based on the question that you've told me that we think X causes Y. And so now kind of draw all the other things that are related to X and Y. And often this also can lead to maybe not a lot of productivity. And then I'll do something like, oh, maybe age should be in there. And this sort of process can sometimes get it going, but it can be challenging to sort of start from a blank piece of paper. So the kind of pros of the expert alone model, which is what we are typically doing now, or at least what I think is commonly done in the biostat world. The pros are that if you can kind of get them to understand what you're trying to do, you have true expert insight. This can work well for small, well understood problems where kind of the data generating mechanism might be well known or relatively well understood. And humans can handle nuance well, so they can sort of understand things like that maybe should go into this. The cons, sometimes there's inconsistency between experts, and so a lot of times you might have inconsistent DAGs depending on who you talk to, and there are certainly ways to handle this, like sensitivity analyses, but that can be challenging. Another con is that it's really not scalable, especially as the number of things that we are thinking might go into these different models, gets larger and larger. In the electronic health record space, we have access to a lot of variables, and they're not always front of mind for different clinicians. And then, of course, the main problem that kind of I am trying to solve right now is just that it's difficult to start from scratch. It's hard to just start with a blank piece of paper and be able to just draw what you think the data generating mechanism is. So the other kind of thing that's happening now, maybe not so much in the biomedical space, but it is kind of happening elsewhere, is this process here where we've got human and robot, which is often like a large language model. So in this case, I might write a prompt to the large language model, and the large language model will say, okay, I will start. And they kind of come up with this, potential DAG for the relationships between X and Y and kind of all other sorts of factors. And there have been a lot of advances in large language models for causal graphs. And I should say that these, a lot of times, like with large language models in general, like when you're kind of 1 minute away from the literature, you're already outdated. So it's hard to sort of keep up because things with these models are constantly changing. But there was a paper by Huntington, Klein, and Ellie Murray that came out. It's on arXiv right now. Last December, they posted it, where they basically showed that large language models performed poorly in a specific setting under specific prompting when trying to kind of come up with these types of DAGs. They're kind of not in response to this particular paper, but I think a potential response to their paper could be Sharma et al. They basically proposed a different prompt strategy where instead of just saying like, tell me what things might cause both X and Y, they had this like triplet prompt strategy, which had this auxiliary variable. And this basically helps because the large language model has like, it's just sort of predicting the next word. It has no context for being able to have like, making sure that there's no cycles, for example, in what it proposes. And so this fixed it a little bit by basically giving 3 variables and saying we have X and Y, and then we have this third auxiliary variable we're conditioning on. And so assuming that we're conditioning on this third variable, describe the relationship between X and Y. And this seemed to kind of help with some of the structural problems and probably some of the problems that maybe Ellie and Nick were seeing there. And it also made it easier to use small models. And so they showed that like the smallest llama model was able to outperform the pairwise prompt, which was just sort of saying just what is the relationship between these two things in GPT. And then Sun and Lee basically proposed starting with large language models and then refining using statistical causal discovery algorithms. And so basically get all the different pieces that might be involved, and then use some kind of statistical algorithm to refine it. And then there have been some early benchmarking efforts that have been trying to sort of take known relationships between variables and look at kind of how large language models or a combination of large language models and humans can do. So the pros of the large language model alone, obviously, in general, it's cost effective, although I know it can be expensive to have different access to models, but these are pretty simple prompts, and so it's pretty cost effective and scalable. It leverages really generalized knowledge, so experts kind of often are in a certain area, which is sometimes preferred, but also sometimes we're dealing with areas that don't have as much expertise yet. So, and it's also effective at extracting kind of local relationships when constrained, like with those triplets. But it can struggle to maintain the DAG structure. When you try to ask it to explain why it had a cause and effect, usually it gives some kind of post hoc rationalization, which is not great. And it's highly sensitive to prompting, which is also not great. So what we're proposing is basically this kind of human in the loop process where you would maybe prompt the LLM would start and give this kind of crazy thing. And then we would tell the clinician to refine it. So it kind of solves that problem of not having anything on the page to start with. So the clinician might erase some arrows that don't really make sense, may add some in, and then we would kind of have the final adjustment set from there. So, coming back to our pros and cons, if the experts refining and the LLMs creating, we kind of solve this problem a little bit where maybe it's a little bit more scalable and, we don't deal with the issues that it's as sensitive to prompting. So this kind of human in the loop approach is what we are trying to do. So we are, this little video is not going to play, but if it were to play, it would show a video of kind of the different structure that we're trying to, the DAG that we're trying to help build with this company C Structure. So C Structure's a company that basically lets you share DAGs across different institutions or between different users. And so they are, we're working with them to be able to run a study that you could look at maybe whether this could work in the wild with experts and LLMs kind of integrating together. So in the last 1 minute, I'll see if I can pull up the slide where I actually do have access to that little video so I can show it. And then I will answer any questions in the last minute while I'm doing that, there are any.
It just says click to exit full screen. Oh, okay. Like, I don't know if it looks like that for you.
Yeah, it was like showing it to me for me, but I don't know if it's like it won't let me do full screen with Safari for some reason. So, but there it is. You can see it moving a little bit. If there are any questions, I'm happy to answer them, but I think I'm at time.
You are about at time. So if you have any questions for Lucy, drop them in the chat. The video is very cool, but we'll let Daphna pull her slides up and move on. Thank you.
Yeah.
Our next speaker is Daphna Harrell from New York University. I'll let you take it away, Daphna.
Thank you. Can you hear me?
Yes.
Yes. Perfect. So hi, everyone. Today I'm going to talk about Twitter, but specifically Twitter in 2013. So back in 2013, there was a change in which Twitter introduced this giant report tweet button instead of this like obscure web form that you would have to find and dig out to report someone's account. Why might you want to report a tweet or an account? For example, if it's posting private information or offensive content, abusive messages, threats, anything like that. So this sort of new content moderation change, we're wondering, does it causally impact the amount of toxic language on the platform? Now, my lab, the NYU Queer Data Lab, specifically works at the intersection of statistics and queer issues. So we wanted to focus on whether or not the policy change, the introduction of this big report tweet button, led to a decrease in the amount of toxic language towards the LGBTQIA+ community. So, the question is, when we see tweets online, how would we rate them? So here are examples of 4 tweets that were posted. And you can see I've blurred out any identifiable information. I've also blurred out some slurs because we don't need to be looking at that. But, there's like 50 of us in this room or something. And if we look at these 4 tweets, we all probably have slightly different opinions as to whether something is like nice or not nice. And if it's not nice, is it really hateful or toxic? Or is it just maybe like annoying and something you don't really want to be reading? Or is it like constitute something that should be removed from the internet? So I asked my lab to do this. We had 125 tweets that we looked at, and we basically, out of 8 people, couldn't reach a consensus on what constituted hate speech or toxic language, because we all had different definitions. We all have our own bias. Also, I just want to point out that me as a professor asking a bunch of students to read hateful targeted tweets is maybe a little iffy on the ethical side. So we need a different way to understand whether or not the amount of toxic language and hate speech decreased on the platform. And specifically, we have 8.5 million tweets that we need to understand, are they toxic or not toxic? And this is just 8.5 million tweets in the year before and after the July 2013 policy change. Now, the astute observer will note that this is a session on LLMs. So how are we going to rate 8.5 million tweets? We're going to run them through GPT-4o Mini. So what we did is we built a custom prompt, like as Lucy was just talking about, the way that you interact with LLMs can be very prompt dependent. So we created this scheme where we would show the LLM some tweet. We would ask it, is this tweet in English? If no, stop. If yes, is it related to the LGBTQIA+ community? If not related, stop. If yes, what is the tone of the tweet? If it's positive or neutral, we would stop there. And if it was negative, we'd ask it, what is the severity of the tweet? Is it just annoying? Can it stay on the internet? Or is it hateful? So for example, we had some tweet that was rated as, yes, it's in English. Yes, it's related. It's negative and it's hateful. And some tweet that was in English, related, positive or neutral. So we didn't ask it the severity question. So what are we going to do with all of these ratings? Now we have 8.5 million tweets, and we have GPT's opinion as to whether or not the tweet constitutes some amount of hate speech. So we're going to look at a causal estimand, which is the difference in potential outcomes at each time point when the tweet was posted of what would be the frequency of toxic language under the old policy, if that was still in effect, that obscure kind of report user form, versus the frequency of toxic language if the new policy is in effect after the new report tweet button was introduced. Now, as in most causal inference methods, or all of them, we have to assume that we don't really know what happens under two scenarios because only one of which is the truth at that given moment. So before the policy change, we have some kind of trend in the amount of hate speech that we notice. Then there's a moment at which the policy is enacted, the new report tweet button comes up, and we want to know, does the slope change after the new policy is enacted? And that's an interaction term in this like interrupted time series analysis. It's this big arrow of did the slope change from the pre-interruption slope to the post-policy change slope. And well, this is what we found. Without too much statistics, you can see that each dot here represents an incidence of hateful language per 100,000 tweets in a given week. And there's some sort of trend that's happening until week 0. This is in July 2013, when the new policy was introduced. And then we see this decrease in the slope, that over time even, the effect gets even stronger, that the amount of hate speech decreased on Twitter in 2013. So there's an evidence that the policy change led to a decrease in anti-LGBTQIA+ toxic language, and the causal effect of the policy change increased over time. But of course, what happens if GPT-4o mini is wrong? I mean, it will be, right? You'll show it some tweets and it'll say that they're fine when actually they're kind of nasty and probably shouldn't be on the internet. And maybe it'll get some wrong in the other direction. But as long as the amount that the measurement error is consistent across time, then our actual estimate will be robust to that, because we're looking at a relative change in slopes and not an incidence or prevalence rate of just how much hate speech there was on the platform. So what we're trying to do now is compare OpenAI to other LLMs, but also to quantify the amount that the LLMs might be mislabeling, given that human annotators cannot really be used as a gold standard, and to look at what type of toxic language is being used. Are they slurs? Is it comparing queer people to animals or diseased or something like that? That's it. Thank you.
Thank you so much, Daphna. We have time for a question, if anybody has one. This is a really interesting project. I'm curious, is the large language model doing all of these like in one sitting? Like, is it learning from the tweets it's already classified in addition to following that flowchart that you showed us?
So we provided the prompt with some examples that we hand selected, but then used the same prompt for every tweet.
Cool.
Great question.
Thank you. Is this work published anywhere?
It just got submitted to a journal.
Oh, cool.
So in an average of 28 days, we'll have some response.
I was just going to ask you to drop the paper in the chat. That's great. Awesome.
Perfect.
Cool. So if there's no more questions for Daphna, I'm our last speaker. So I'm going to switch my role really quickly and share my screen. So there's been a lot of really interesting discussions so far around how we can bring large language models into our kind of existing statistical research and use it to kind of make them better. So my background is largely in two-phase designs to monitor data quality, which means I do a lot of dealing with missing data and measurement error, primarily in observational databases like the electronic health record. So at a very high level, electronic health records contain routinely collected patient data. In the United States, upwards of 90% of all primary care and hospitals now rely on electronic health records. And so every time you go to the doctor, you become a series of data points in the EHR. And basically, as these data have accumulated, people are starting to catch on that there's a lot of really important ways we can repurpose them. For example, large scale analyses where our data come at little to no additional cost for research, for collection. Now, the inherent cons about EHR and routinely collected data are that they're collected in the fast-paced world of clinical care, which means that they're prone not only to measurement error, but also to informative presence bias and informative missingness. For example, a doctor isn't going to order a lab just because we want the data. They're going to order a lab because they think it's clinically indicated. And so in this talk, I'm going to focus just on missingness as one of these cons. Now, a lot of my work with the EHR has involved expert chart reviews, which is where we extract some version of the data for our study from the electronic health record, and then we have clinical experts like research trainees or research nurses who go through and manually compare what we got from the extracted data to what's in the original electronic chart, where whatever is in the chart is presumed to be more accurate simply because it's closer to the point of care. Now, these chart reviews are incredibly valuable. They uncover information about quality and also opportunities for process improvement, but they're resource and time intensive. We ran one a couple of years ago that required a team of 4 auditors and over 100 hours of human expert effort to review 100 patient data on 10 variables. So this is a non-negligible investment. So our objective today was to compare an algorithmic approach to chart review. Can we see how an algorithm based on a clinically driven LLM enhanced roadmap relying on structured EHR data like disease codes compared to what our human auditors found in that project? Now, the motivating example for this project is our health system's interest in adopting a whole person health score that can be operationalized across the entire healthcare system. So specifically, we're interested in the allostatic load index, or the ALI, which is a 10-component whole person health score. A lot of these 10 components are possibly captured in the EHR, but not for everyone. And even when they are, they're sometimes going to be imperfect. And so in a previous study, we extracted 1,000 patients at random who were chosen based on 2 criteria. They had to be adults 18 to 65 years old, and they had to be newly engaging in routine healthcare, meaning have a primary care visit in the 2-year period right up before COVID. And so on average, patients in that original data pool had 6 of the 10 non-missing ALI components, but the interquartile range varied between 5 and 7. And you can see that in particular, some of the missingness is admittedly pretty severe. Over here, these 3 values are inflammatory markers, and these labs are incredibly uncommon because your doctor won't order them unless there's some indication that you needed it. And so we knew that missingness was definitely a problem in this data pool. And so a subset of our original study, 100 out of 1,000, were chosen to undergo additional expert chart reviews by clinical research trainees. And our thought with this was, could we use the chart reviews to double check the integrity of the non-missing values and also take advantage of some additional information in the electronic chart to try to uncover some auxiliary information for these missing components? So the ALI, like I mentioned, is made up of 10 components. They're listed here in this table, and they represent 3 different body systems: cardiovascular, metabolic, and inflammation. Basically, you take these different components, which are biomarkers, labs, and vitals, and you take them either at a discrete time point or averaged over a study period, and then patients' values are thresholded into an unhealthy or a healthy category. This is a classic definition of this score. We're very interested in additional versions, but we're trying to basically make the existing one work before we get too much fancier. And so we take these measures, we threshold them, and then the idea is that they get summarized into the ALI. And so what we did in our previous project was we worked with clinicians to try to come up with information like if hemoglobin A1C is missing, is there anything else we can look for or have the experts look for in their chart that might have indicated that that missing hemoglobin A1C would have been unhealthy? We can't find a lab that was never run, but we were trying to figure out if there were additional sources of information in the electronic chart that could help us understand the underlying kind of decision making. And so they came up with search terms for 9 of the 10 components. Serum albumin was kind of tricky. We didn't have any for that one. And these are the 20 search terms, and we gave those to the clinical reviewers. And with this roadmap, they recovered 45 of 413 missing components across those 100 patients. And with this, we did see an improvement in the average number of non-missing components among those 100 to 7 out of 10. But what about the other 900 patients? So previously we used this to fit an inferential model, moved on and said, well, yeah, the ALI is associated with kind of clinically meaningful outcomes. But that really only gave us interpretations at like an inferential or a population level. But in terms of actually better estimating ALI for everybody, we were interested in more scalable ways of using this roadmap-driven data recovery. And so what I realized was that all of these search terms are actually things that are captured in structured fields in the EHR. These are things that are largely captured by the International Classification of Diseases codes. And so the first version that we tried, or the general flow of our missing data recovery algorithm, starts with a roadmap that maps the components to informative search terms. The search terms then get merged into the ICD codes so that it'll be easier to actually look for them. And then we take the ICD code version of the roadmap and merge it into the patient's diagnostic data and use that to basically simulate the chart review process. So we tried this algorithm with 4 different roadmaps. The first was the ones that our clinicians had come up with for the original project. This had 20 search terms. And then we tried 2 large language model enhancements using the Elmer package in R to query Google's Gemini. The first one we call LLM baseline. This point has come up a lot today. It matters what and how you set up the large language model. The baseline one was given very little information. It was basically told if serum albumin is missing, what would be helpful for it, and we think higher values are unhealthy, for example. This one might not surprise you, it did terribly. The LLM with context, however, was asked to do the same thing, but it was given the examples from the clinician's original roadmap. It was basically told, these are the search terms that we think are helpful. Would you like to build upon this list? And so this proposed the most terms, and we thought that a lot of them would be clinically relevant, but there was no guarantee that they all would be. And so our final roadmap actually gave that LLM enhanced version back to the same 2 original clinicians to create kind of a nice feedback loop. So now we took the clinician's roadmap, gave it to the LLM with context, then gave that back to the clinicians so that they could adjudicate whether or not the additions by the large language model actually really belonged and were relevant. And so to quickly summarize the performance, there were originally 413 missing components across these 100 patients in our EHR. The chart reviews recovered 45 of them, or 11%. Using the clinician's version of the roadmap, recovered slightly more, and actually that discordance was because there were some diagnosis codes that technically matched, like infection could be something like an acute respiratory infection, but actually in terms of your body's response and the relevant component of the ALI, the chart reviewers probably decided that that wasn't really an appropriate one. The LLM with baseline barely recovered anything at all, 3 out of 413, while the LLM with context actually recovered the most simply because it had the most search terms. The LLM with context and clinicians recovered the exact same amount as the experts. And so it kind of brings us full circle and allowed us to get agreement between what the humans found and what we were able to operationalize using the algorithm. And so we took this kind of best algorithm and scaled it up to the full 1,000 patients. Across them, we recovered a similar proportion of about 13% of missing components. After augmenting with the algorithm, it did bump the median allostatic load up a bit, indicating people were a little less healthy on average once we'd recovered missing data. The median number of non-missing components went up now for everybody instead of just the 100. And finally, there was a very informative, strong correlation between the ALI after the algorithm with the EHR. And that's important in terms of measurement error corrections and if you wanted to kind of harness this information in conjunction with the chart reviews. So I'm out of time, but this paper is recently up on arXiv if you'd like to read more about our work. And shout out to Lucy, who was also on this paper. Thank you all for coming to the session.